Alright, so here in this video, I have a few angular momentum, angular impulse MCQ questions for you to practice. The first one being this one. It says you're given a graph of torque versus time, and it says which of the following claims about angular impulse, again, the question here is on angular impulse, is true. Alright, so you're given a torque versus time graph. So in order to find angular impulse, you first have to recognize that you're asked really to just assess the area of this particular graph, because the area underneath a torque time graph is angular impulse or change in angular momentum. Okay, so here is the function for it. Net torque times change in time is equal to change in angular momentum, which is known as angular impulse. So really you're looking for delta L. How do you know what delta L is? Just find the area. Alright, so I made a note for you here. Area of this particular torque time graph is angular impulse, also known as change in angular momentum. Well, this graph is pretty nice, as you can see. There's no trick traps here. The first area I'm going to shade is from 0 second to 5. It's going to go up 2. And the second area I'm going to shade above the t-axis is this triangle. However, on the bottom, that is very symmetrical. This triangle is really just the other triangle that's flipped upside down. And then the last rectangle here is the same as the first rectangle I drew. So angular momentum is a vector quantity, so it has to have a sign or direction. So if the area is above it, it's positive angular impulse. If the area is below it, then it's negative angular impulse, or the change in angular momentum is negative, and here the change in angular momentum is positive. But as you can see, all these shaded areas are equal in magnitude. So really, if you sum up these two values, or sum up the two shaded areas above and below, you get 0. So while the object changes during 0 to 5, 5 to 10, 10 to 15, and then 15 to 20, overall for the 20 seconds, it actually cancels each other out. So it's actually going to leave you with a change of 0, because the two areas perfectly cancel out for this particular graph. So I'm just going to say that the angular impulse is 0, because positive, let's say a positive 5 here or negative 5 cancels out perfectly. Okay, all right, I'm just using 5 as an example. Same magnitude, just opposite direction. All right, let's do this next one. Here you have two forces of equal magnitude that are exerted at separate times. And then it says the board is initially at rest and is free to rotate about the axis at the end. So if you need to pause, read it. Essentially, you give here two figure before and after, figure 1 and figure 2. In the first figure, the force here is being applied at the center of mass of the board. On the second figure, the force is being applied at the very edge of the board at an angle. And you're asked to find the what is this? The ratio of the final angular momentum of the second scenario to that of the first. Okay, so I'm just gonna do this in order from left to right. To find angular momentum, you have to apply net torque equals times time. The reason I want to start with this function is because you're given a force, the problem gives you a time, and you have to find, the final angular momentum. So this is exactly what you need, because everything is given. Well, to do torque, you need force and R. Here, your force is being applied at the center. I don't know what R is, so I'm just going to go ahead and call the length of the board here is L. Okay, I don't need L though, because here the board is midpoint, and so I'm just going to call this segment from the axis of rotation to where the force is being applied. That's just half the length of the board, so that's just L over 2. So I can just plug these values in. Well, net torque is force times R. Force is just F here, because that's what the diagram gives us. And what's your R? R is L over 2, because it's measured from the axis of rotation. So if you watch my cursor from the axis of rotation to where the force is, that's L over 2 in the X direction. F is already in the Y direction, so that's already perpendicular, so I'm done there. I don't need to find any components. Well, what's my delta T? Delta T is given as, what is this, 2T, whatever 2T is, okay? So I'm circling back and forth here. That's 2T in the problem, in the figure 1. On the right side, I'm going to break up change in angular momentum to LF minus LI, but here there's a 1 because this is figure 1. And then I'm just going to cross out L1I because the problem states that it starts at rest. And then I'm also going to cross out the 2 on the bottom and top on the left side, just because 2 and 2 cancels out. So the only thing left on the left side is FLT, and the only thing left on the right side is L1F. Okay, so now that I have an expression for L1F, I'm halfway there. I need to find what L2F is, because that's what I need to compare to L2 to L1. So I'm going to use the same function here. However, this particular force is being applied at an angle. All right. The length of the rod is already in the x-axis, which is just capital L. I need Fy. Fy is perpendicular to the R. Okay, so here I'm just going to break this F into its two components, Fx and Fy. However, the only force component I need for this particular torque problem is Fy. So here's the length of the rod, here's Fy, and Fy by definition is F sine of 60. I want to assume that this 60 degrees is touching the x-axis. It never said that this angle touches the vertical axis. So if it doesn't, normally we like to assume that the angle given touches the x-axis unless otherwise stated or drawn for you. Okay, the 60 is kind of placed here vaguely, so I'm just going to go ahead and use the angle touching the x-axis. Now, if this angle happens to touch the y-axis, then your answer changes because it dictates whether you sine or cosine. So here in my work, because I'm going to assume that the 60 degrees touches the x-axis, y is my opposite leg, and opposite triggers the sine function. Okay, so Fy here is just F sine of 60 degrees. So Fy is perpendicular to L. So I'm just going to go ahead and apply this to my net torque times time equals the change in angular momentum function. So net torque, once again, is just F times R. And here my F is Fy. I just enlarged that for you. Fy is perpendicular to L because L is in the x-axis. So here I'm going to say F sine of 60 because that's Fy times L, which is quote unquote my R. And how much time? Well, time is just t. The second scenario says you're just applying for a time t, whatever t is. On the right side, I did the same strategy. I just broke it up, and then I'm going to cancel out L2i because the system starts at rest in both of these scenarios. So here, sine of 60, if you want, you can keep in radical, which is radical 3 over 2. And if you don't know, I'm sure you can look this up if you like, because I notice here all the answers has like a nice numbers. Okay. So here I have an expression for L2F, which essentially is just radical 3 over 2 FLT. So I'm just going to go ahead and pull the coefficient to the front, the radical 3 over 2. I'm just going to put it in the front, times it by F, times it by L, times it by T. So I'm really not doing anything here except for rearranging it just so it looks nice and neat in the same order it is on the left side. All right. Other than that, how do I get it to what the question wants? I'm just going to write L2 to L1 because that's what the question is looking for, the ratio of L2 to L1. Well, L2 is radical 3 over 2 FLT. L1F is just FLT. As you can see here, FLT on both sides cancels out this ratio. So essentially, you're just left with radical 3 over 2 to 1. However, the question here wants L2 in terms of L1. So I can just multiply both sides by the reciprocal of 2 over radical 3 just to get this side to be a 1. And then 1 times the reciprocal is just 2 over 3, or 2 over radical 3. And at this point, hopefully you see that it's choice C. I think you could have stopped your work if you were really thinking about it. The only answer that mirrors anything that has a radical 3 over 2 here is choice C. All right, let's move on to the next one. Here you have a wheel that has a rotational inertia of 2 kilograms meter square. And it says it has an initial angular velocity of 6 rads per second in the counterclockwise direction. And then there's a torque that has a magnitude of 5 newtons times meter that's also acting in the same counterclockwise direction. So here your torque is acting with you, not against you. So the object is going to speed up, right? Okay. So if your angular velocity is counterclockwise and your torque is also counterclockwise, the torque is acting with you, which will cause the object to speed up. So by this time, hopefully you've understood these concepts from your linear days. All right, so the problem here states that the torque is going to apply for 4 seconds. The first part of this particular question asks you what is the change in angular momentum. Well, to find change in angular momentum, once again, you would just apply the net torque times time. That equals the delta L. Here, net torque is given as 5. And I put a positive sign here because counterclockwise is positive and then clockwise is negative. So it's important that you understand that there are directions for torque as well. Okay. Time here is 4 seconds. The problem said so. Now, if you don't understand positive and negative torque, again, here's positive torque going in the counterclockwise direction, and then going in the clockwise direction is negative torque. All right. And then that, really here you're kind of done, right? 5 times 4 is just 20, so you might as well just stop there. The answer here is pretty straightforward. But if you want, I just broke up the units here for you. Newtons is mass times acceleration. The unit for mass here is kilogram. The unit for acceleration is meter second square. And then the second square here is going to cancel with that second there. So it leaves us with the same unit that the answer has it in, because the answer has it in kilogram times meter square per second. But in terms of just the magnitude, it's just 20 from the get-go, okay, because 5 times 4 is 20. All right, the second question of this particular question asks you what is the angular momentum at 4 seconds. So all you have to do, it really is just use this particular function. Delta L is LF minus LI. We already know, what LF is, what LI and the change in angular momentum is, because all the stuff we already calculated or is given. So to find LF, all you have to do is add LI to both sides, and then that looks like this. The change in angular momentum plus the initial angular momentum is equal to the final angular momentum. We already found the change in angular momentum in the previous part, which is positive 20. And then what is Li? Li, by definition, is just the moment of inertia times the initial angular momentum. And then here, moment of inertia is given as 2. And then your omega I, which is spinning in the same direction as the torque, which is positive because it says counterclockwise. So here I highlighted a direction for you. We know that's going to speed up because the torque is acting with the angular velocity, not against it. So we know that it's going to speed up. Speeding up would cause the angular momentum to increase. Okay, so here this is 20, and then plus 2 times 6. 2 times 6 is 12. 12 plus 20 is 32. So I'm just gonna go ahead and highlight choice E. Okay. All right. Let's move on to the last one in this particular video. Here's a really wordy question for you. Essentially, you're given an angular velocity graph versus time. And it says one student in the group states that the graph shows that a net torque is exerted on the rod because the rod's angular momentum is increased. And it says, do the data support the student's statement? And then it wants you to justify your claim. Well, here you're given an angular velocity versus time graph, and you're given really a data set here that kind of resembles slope, right? So I do want to point out that the slope of a velocity time graph is your acceleration. Well, if you're accelerating, the object is either speeding up or slowing down. In this case, the initial angular velocity is 0, and then it increases to some value. What is this? 400 rads per second. So which would imply that angular acceleration is positive because this is a positive slope. All right, so to do this one, again, you would just apply the functions I've been playing with the last few slides here. Net torque times time equals change in angular momentum. And then we know that change in angular momentum is just LF minus LI. Okay, and then we can expand LF into I omega F because angular momentum is just moment of inertia times the angular velocity. And then Li likewise is the same. I, whatever this rod system is, times its initial angular velocity. Okay, so again, we're just looking for which statement makes sense. And then here, I made a note for you. Net torque is equals to I alpha. Why is this important? Because to have a change in angular momentum, you need some sort of net torque. Well, to find net torque, you need a moment of inertia times angular acceleration. Well, just by looking at the graph, there is an angular acceleration because the velocity is increasing, which means if velocity is changing, alpha has to exist. Okay, so watch my cursor. Well, we know that A exists. We know that I really is, well, there's a rod, so there has to be some sort of moment of inertia. So if there's an alpha and there's an I, there has to be a net torque. Well, if there's a net torque over some time, there must be some sort of change in angular momentum because the velocity is changing. The angular velocity is changing. So therefore, the only answer that makes sense to me is A. It says yes, because the angular velocity increases with time. Therefore, the angular momentum of the rod increases. Well, yeah, angular momentum depends on angular velocity. So if angular velocity goes up, angular momentum has to go up. And it says this can only occur as the result of a net torque. Well, fundamentally, we say that angular impulse only exists if there is a net torque. Well, how do you know if there's a net torque? There's a net torque because there is an alpha. If there's an alpha, there has to be a net torque. So therefore, I'm just going to pick choice A, and I'm just going to bypass all the other answer. Okay, that's it. Or if you want to, I mean, B just makes no sense. It's just the area bounded, between 0 and 10 is positive value. But it says, therefore, angular displacement of the rod is non-zero, which is true. It is non-zero because it's some value. But this last part is kind of funky. It says this can only occur as the result of a net torque. Well, not really. You can move at a constant velocity and have a positive area. Just because you have a positive area doesn't mean you have a net torque, because you can have a positive area and be moving at a constant rate, and if you're moving at a constant rate, there is no angular momentum. So this justification kind of, I think, falls short of that. And in C and D, it's kind of whack. Okay, so if you know your torque, I think A just kind of sticks out. All right, I hope that helps. Stay nerdy, don't be whack.